Now let's talk about how we can use Monte Carlo simulations to study the power of a hypothesis test. By definition, the power of a hypothesis test, H0 versus H1, is the probability of rejecting H0, the null hypothesis, given that the true distribution is H1. In other words, we usually denote power by 1 minus beta, where beta is the type 2 error. And this is given by the probability that the test statistic is inside the rejection region C, given that H1 is the underlying distribution. Typically, we would like to control our type 1 error level at a preset level, say alpha equals 2.05. And given this constraint of the type 1 error below 0.05, we want to achieve a sufficiently high power. Usually, the power of a test, which is the probability of rejecting the null given that the alternative is true, depends on the sample size of your test statistic, so how many n's you have, as well as the particular value of the parameter underlying your distribution of x. So in this case, the theta belongs to the set theta 1, which is corresponding to H1. One thing that's really useful is power analysis. So power analysis is often conducted to determine sample size for a study. In other words, given a hypothesis testing procedure, some T and critical region C, with a fixed level of type 1 error rate alpha, what is an adequate sample size so that the power can be greater than or equal to 1 minus beta? So power analysis is one of the must-have skills as a statistician, especially if you're a biostatistician or anyone who works with collecting empirical data. Power analysis can be useful particularly for a few things. The first is clinical trials. So in this case, for example, we want to study what is the effectiveness of a new treatment or what is the effectiveness of a new COVID vaccine. In this case, we want to do clinical trials where we do, after collecting the data, we would like to perform all sorts of tests, such as the log rank test and the Cox proportional hazards test, which are very commonly used for biostatistics. In these cases, when you're proposing your study, so before you collect any data and administering people the treatments and controls, you probably want to decide how many samples do you want to collect. On one hand, you don't want to collect, say, too many samples because that's going to take you a long time and it's going to be really costly. On the other hand, you want to have a sufficient sample size so that you know if the null hypothesis that the treatment is not useful is actually not true, then we have a great chance of actually rejecting the null. Another situation where power analysis can be really useful is for grant applications. So whenever you submit a grant proposal, for example, to the National Science Foundation, so the NSF, if your study involves collecting empirical data and doing some hypothesis testing, often doing some sort of power analysis is a must. In this case, when people review your grant application, they want to make sure that the study you are proposing and the sample size that you're hoping to collect under this proposal is sufficient to avoid underpowered studies. In other words, the government will not be happy if they funded you $1 million and then after 3 years you say, oh, the result is still indecisive because I probably didn't collect a sufficient sample size. So in these cases, the power analysis can be really useful for us to determine what is an appropriate sample size. Let's see how we can use Monte Carlo estimation to estimate statistical power. The procedures for doing this is actually very similar to that for the estimation for the empirical type 1 error rate, which we just did earlier. The only difference is that we want to generate our random samples, x's, not from the null distribution, but instead under H1. Because for power analysis and the calculation of power, we are interested in the probability of rejecting the null given that H1 is true, instead of under the null hypothesis. Otherwise, everything is pretty much the same. So again, for replications j from 1 to m, we want to sample x1 of j all the way up to xn of j, so a sample size of size n, under the alternative distribution. In other words, given some theta, the underlying parameter, that belongs to the set theta 1. Based on this random sample, we again calculate the test statistic t for the j replication. And then we perform the hypothesis test and see whether our t this time is inside the rejection region. If yes, then it's going to be equal to 1. This indicator is going to be equal to 1, meaning we reject the null. If not, we retain the null, and this is going to be equal to 0. Then our power for this procedure can be estimated by the proportion of times the hypothesis is actually, the null hypothesis is actually rejected. In other words, the percent of times that the test statistic is in the rejection region. This gives us the proportion of times H0 is rejected when the data comes from H1. Let's see an example of power analysis for testing the Pearson correlation between two normally distributed variables. Suppose that we have x and y, which are bivariate normally distributed with correlation given by rho. By definition, their correlation is equal to their covariance divided by the square root of the product of their variances. This can be estimated with samples. So suppose we have random sample of size n, x1, y1, etc., all the way up to the pair xn and yn. Then the sample correlation estimate, also known as the Pearson correlation coefficient, is given by this formula over here. This is something you should have seen in your first statistics course. And in case you don't remember, this thing is going to range from -1 to 1. If it's equal to 0, it indicates that the two things are not correlated. Once it gets closer to 1, it means that the correlation gets stronger. And if it's negative, it means that x and y are negatively correlated. Otherwise, if it's positive, then x and y are positively correlated. All right, so what is the hypothesis we want to test? We want to test the null hypothesis that rho is equal to 0, meaning x and y are uncorrelated, versus the alternative hypothesis that rho is not equal to 0. So you might wonder what would be a test statistic for this. This is something you might have learned before, or you might not have learned this before. So one way of doing this hypothesis test for H0 given by rho equals 0 is computing the test statistic T, which is equal to the correlation between x and y times the square root of m minus 2 divided by 1 minus r squared. Under the null hypothesis that x and y are indeed uncorrelated, T follows the T distribution with n minus 2 degrees of freedom. So to use power analysis for determining sample size requirements, we usually need to first specify a minimum level of power we want to achieve to test a difference from the null that is of scientific interest. Taking our example of testing the correlation between x and y, here, what we want to determine is, so here's an example of what we want to pre-specify before doing the power analysis and figuring out what is a good sample size. So here we might ask, given a hypothesis test with type 1 error rate of some alpha, say alpha equals 0.05, if the true value of rho is equal to 0.5 or something higher, then how large does our sample size need to be to achieve a power of at least 0.8? In other words, if the true correlation between x and y is non-zero and it's something above 0.5, then what is the sample size we need so that the probability that we rejected null is higher than or equal to 0.8? What we can do is to try different values of the sample size and rho, and we can see how the Monte Carlo estimate of power for testing the null hypothesis changes. Again, we would like to do a mini simulation study where we simulate the hypothesis test under different conditions of sample size and different conditions of true correlation between x and y. We will consider sample sizes of 10 to 100 with increment of 10 at each time. For the true correlation between x and y, we will consider the case where they are uncorrelated 0, and then 0.1, 0.2, all the way up to 1. Note that we're not considering the case where rho is negative here, but if you want to do that, that is fine as well. Again, we would like to start by creating an empty matrix for storing our results. And our results will be the proportion of times H0 is rejected under each condition of n and rho. So first, let's tell R this is the sequence of n's sample sizes we would like to consider. And this is the sequence of correlations between x and y that we want to consider. So the sample size ranges from 0 to 10 to 100, and the correlations is from 0 to 1. Now let's create a matrix called pow. And this is a matrix of all NAs at this moment. The number of rows is equal to the length of the n's vector, meaning that there is going to be a number of rows that is equal to the number of sample size conditions. The number of columns is equal to the length of the rows vector, meaning that each of the column will correspond to one of the possible rows for generating x and y. Again, we give the row and the columns names like this so that the table is easy to read. So just like the case for the t-test, let's create a function for testing the hypothesis first. Note that we want to test the null hypothesis that x and y are not correlated versus the alternative hypothesis where the correlation is non-zero. And the test statistic we're going to use is given by this thing over here, which we know that it should be t-distributed with n-2 degrees of freedom. And because it's t-distributed with n-2 degrees of freedom, we can use that to find out the critical values for our particular alpha level of 0.05. So here's our core decision function, where it takes elements, inputs x1 and y and the type 1 error rate, and then it outputs you the decision of whether you reject a null or not. First of all, based on our x, y's, so the inputs, we can figure out what is the sample size. And then we can calculate the Pearson correlation between x and y using the core function applied to these two length n vectors. Then we can calculate this test statistic. It is equal to r, the Pearson correlation, times the square root of n-2 divided by 1 minus r squared. What we want to do next is to compare the test statistic with the critical value given by the t-distribution. So the critical value is again Qt. So the 1 minus alpha divided by 2 quantile, with where the t distribution has a minus 2 degrees of freedom. If our absolute value of the test statistic is greater than t star, then in this case we want to reject the null. Otherwise, we accept the null hypothesis. In the end, we return the 0 or 1, indicating whether we accept or reject the null hypothesis that the correlation is equal to 0. Now, we can simulate xy with different rho values ranging from 0 to 1 and with different sample sizes. And then we can calculate the proportion of times the null hypothesis is rejected across the m replications. So here let's use an m of 1000, meaning that we will repeat each condition for 1000 times to approximate the power. For simplicity, let's use the RMV norm function inside the MVT norm package to draw xy's from the bivariate normal distribution. In week 2, we learned about how we can do this from scratch, but maybe we can save some time and space over here. The RMV norm function allows you to draw random samples from the multivariate normal distribution for given mu and covariance values. Because we know that the correlation is invariant to the mean and the variance of x and y, we will just, without loss of generality, assume that x and y both have mean of 0 and they both have standard deviation of 1. First thing to do is to load the MVT norm function package. And then we will tell R that the M, which is the number of replications we want to do, is equal to 1000. Our mu for generating x and y is equal to 0 and 0. And then the alpha level, the significance level we want to do is 0.05. So for this set of loops over here, what essentially it does is for each sample size and rho condition, we try to find out what is the decision, which is to reject or retain the null for each of the m replications. So across the 1000 replications, every time we simulate or we randomly draw x and y using the RMV norm function, the sample size will be equal to the ith value of the nth vector. The mean is given by mu, and the covariance is given by the matrix where the diagonals are equal to 1, indicating that the x and y are both having variance marginal standard deviation of 1. And the off diagonals, which is the correlation between x and y, is given by the rth entry of the rows vector. After we draw the x and y's, what we can do is given the sample, so the first column of x dash y is x values, and the second column is the y samples, and given our alpha value of 0.05, we perform the hypothesis test for that iteration and see whether we reject the null or retain the null. And then for that particular sample size and rho condition, the power that we estimate using Monte Carlo simulations will be the mean of the decision vector. That is the proportion of times that the null hypothesis is rejected. So there's one thing I'm not mentioning over here, which is related to the standard error of the power estimate. Since this is still a proportion and a sample mean, the usual standard error estimate formula for the sample proportions still apply. So you can use the same formula as you did for the case where you're trying to calculate or estimate the empirical type 1 error rate. Okay, so let's look at the results. Here is the Powell matrix, rounded to 2 digits. And each column represents a possible row level. So that is where our x and y's are generated. So the underlying true distribution or the true correlation between x and y. This ranges from 0 to 1. Each row is a sample size condition ranging from 10 to 100. So note that the first column, which is the case where row is equal to 0, actually gives us the empirical type 1 error rate. That is, when the x and y are truly uncorrelated, what is the proportion of times that we tend to reject the null hypothesis? And we can see that all of them are quite close to the theoretical value of 0.05, which is good. So based on this table, you can try to find some patterns and see how the power changes as we change our n and the true correlation between x and y. One thing you might observe is that as your correlation gets stronger and stronger, the power of a test increases. Also, as your sample size gets larger and larger, your power also increases. Recall that our problem was to find out, given that if the correlation between x and y is 0.5 or larger, what will be a sufficient sample size n so that we can achieve a power above 0.8. So based on this table over here, we can find out that when n is somewhere between 20 and 30, this is when we can achieve a power of around 0.8. So you can see that for the 0.5, rho equals 0.5 case, when n is 20, our power is 0.64, which is lower than 0.8. And when our sample size is 30, our power increased to 0.82, which is slightly higher than 0.8. What we can do next is to look at all possible n values. So now we're narrowing down our range to values between 21 and 29 for sample size. Let's look at all possible sample sizes between 21 and 29 and see at which point can we achieve the power of 0.8. You're going to need to fill in the code for this part yourself, but everything else is actually quite similar to before. The only thing we need to change when we change the sample size from 21 to 29 is we want to change the n's conditions. Instead of testing from 10 to 100, we do 21 to 29. Everything else is the same. We still create a PAL matrix for storing the results. And then for each of the possible n's and possible rows, we try to see what is the proportion of times we reject the null. And here are the results. You can see that when n is approximately 28 or 29, this is the case where the sample size seems sufficient to achieve a power of 0.8. So in practice, I will be slightly more conservative. So for example, if you get a 28 that is close to, say, something that runs to like 0.79 or 0.8, and for 29, it's 0.81, which is higher than 0.8, I will go with the larger sample size so that your study does not become underpowered. So I just illustrated how we can use the power analysis to figure out what is an appropriate sample size if we want to achieve a particular power level under some particular true alternative distribution. Another thing that's quite useful is the plotting of power curves. Empirical plots for power are often quite useful for visualizing how power changes with respect to either sample size. In that case, you fix the underlying theta to a fixed value. So for example, rho of 0.5, or how it changes with respect to theta. So in this case, you fix the sample size and see how the power changes as you change your theta value. For example, given a sample size of 28, we can plot a power curve where we change our theta, in this case our rho, the true correlation between x and y, and see how the statistical power, which is the probability of rejecting the null, changes when the true rho ranges from 0 to 1. For plotting this, we will consider smaller increments of the correlation. So in this case, we're going to have a sequence from 0 to 1, but this time with increment of 0.01. And then after calculating the power for each of these possible rows, we can create a scatter plot where the x-axis is the rows and the y-axis is the corresponding power when n is 28. And here's the code for computing the powers for each of the rows. This time we create a rows vector that is the sequence from 0 to 1 by the increment of 0.01. Our sample size is fixed at 28. This time we can create a PAL. Since we only have one sample size condition, PAL can now be a vector whose length is equal to the number of entries, the number of possible rows. And then for each of these possible rows, we try to figure out what is the proportion of times that we reject the null hypothesis. So just like before, we iterate this for 1,000 times for each row. And for each time we sample our data, x and y, from the multivariate normal distribution with mean, mu, and sigma, where rho is given by this value between 0 and 1. And then we perform the hypothesis test. So here's the scatter plot. Like I said, the x-axis is the rows ranging from 0 to 1 at the increment of 0.01, and the y-axis is the power, which is the proportion of times out of the 1,000 times that we rejected the null when the row is given by this particular value. I'm setting some graphical parameters here in my code. So PCH of 19 means that I want to plot the dots as solid dots. And then CX equals 2 is for adjusting the size of each of these dots. If you don't do this, the dots are going to be really large. And if you don't do PCH equals 1, it will be many circles on this plot. Yeah, so if you don't change PCH to 19, by default, the points are going to be little circles on the plot, which doesn't look so much like a curve. So you can see that in this case, it seems like the power actually follows a smooth curve. There are some minor fluctuations, which are possibly due to the Monte Carlo standard, because the randomness of the Monte Carlo estimation. And over here from the power plot, we can see that when the correlation is around 0 between x and y, then the power, which is the probability of rejecting the null, is probably somewhere close to 0.05. And then it keeps increasing and increasing. And when the correlation gets really high, we almost always reject the null hypothesis. And you can also see that when rho is about 0.5, the power that we estimated using the Monte Carlo techniques is quite close to 0.8. So that's consistent with our earlier results. All right, so that is it for Monte Carlo inference. You might be getting a little bit bored at this point and thinking, geez, I've probably calculated, say, 100 sample means at this point. Well, starting from next week, we are going to get started with something different. So we're going to talk about bootstrap and resampling methods. This is the case where we are given observed data. However, we do not know what is the underlying true distribution. So in this case, how can we try to numerically find out what is the distribution of a test statistic?